First of all, I want to thank Professor Bala Iyer to give us the time and be available to deliver this talk on deciphering the universe with gravitational waves. I also want to thank the participant online and offline for joining late evening. So I always want to organize talk by Professor Bala Iyer, but the most difficult part I find is how to introduce him. Most of the time, I feel that why there's a need to even introduce him. It's like as we say in as the saying in the Hindi goes that it's like Suraj ko diya dikhane jata. I mean, but I still try to figure out something, and then I stumble upon CV of Professor Bala Iyer, and it's a pretty long CV. It has 53 pages, and I'm sure that so many pages are still left either to be written or they are missing from the CV. So Professor Bala Iyer, if I want to write, tell in one sentence, then he is a leader, he is a mentor, he is a teacher, he is a profound researcher, and he is a fantastic human being. This is about him. If I talk about his professional accomplishments and achievements, he has been leading the efforts of bringing the LIGO detectors to India. He has been working on the gravitational wave physics since his PhD, and that should be around 1970 or maybe earlier than that. So he has been currently at ICTS-TIFR Bangalore as a visiting faculty. Before that, he spent a very good time, a long time at Raman Research Institute. If I want to tell you a few interesting things from his CV, the important thing is, that interesting thing is, if you look at his list of the referee, these are Kip Thorne, Tamur, Bernard Schutz, and Stan Whitcomb. So these are all the leaders who are leading the effort across the world, in US, in Europe, and other places. Professor Bala Iyer, as I told you, he has been instrumental in proposing the LIGO India on the Indian soil, and he has been dealing with the government. He has been organizing so many workshops to the younger generation. He is training the PhD student. He is working closely with the other faculty members. And in fact, he was just talking about creating new generation for the gravitational wave community. He has already trained a few good PhD students. A. Gopakumar, he is a TIFR. KG Arun, he is at CMI Chennai. And Chandrakant Mishra, who is at IIT Madras. And I might be missing few of other students also. So Professor Bala Iyer, his research interests, they lie in gravitational uh, modeling, the calculations of gravitational radiation coming from the compact binary coalescence, and so on. He has published a numerous number of papers. He is recipient of several awards. The most prominent, I can name a few. He is basically the fellow of American Physical Society. He is fellow of International Society of General Relativity and Gravitation. He has he has won the Special Breakthrough Prize in Fundamental Physics. He also has several other awards. He is Vaidya Rai Chaudhary Endowment Award given by IAGRG in 2015, Beller Lectureship for APS April meeting 2015. So the list is very, very long. I can probably share his link to his CV where you can know more about him. He has held several positions. He has worked in all the, fantastic labs across the globe. He has spent time at Washington University, University of Wales, Max Planck Institute in Germany, ICTP, ICTS is currently there. He did PhD from University of Bombay, and then he spent postdoc and did postdoc in France. I think that was a group of Damour, if I'm right.
Yeah.
In France, yeah. And he has worked with the other big names in the community. leading GW theorist, including Cliff Will, and he has been the editor-in-chief for an online journal, very, very prestigious journal, on living review in relativity. I can go on, but I know people are waiting for talk. So without further ado, I will like to give it over to Professor Bala Iyer. Sir, over to you.
Thank you, Gurudat, for your kind invitation and your kind introduction. So let's get started. So the title of my talk is Deciphering the Universe with Gravitational Waves. What I'm going to talk to you is a work of a very large collaboration, the LIGO scientific collaboration, the Virgo collaboration, and KAGRA. The funding agencies are the NSF and the corresponding agencies in Europe and Japan. This is the plan of my talk. I begin with a primer on gravitational waves to remind you of some technical aspects. Then I come to the discoveries and the breakthroughs which came, the consolidation of that, the current status of the field, and finally, where are we headed, the future prospects. Gravitational waves are freely propagating oscillations of the gravitational field. Physically, gravity manifests as a tidal effect. So we can say gravitational waves are oscillating tidal gravitational fields which propagate out from the source. A measure of the gravity wave strain is a quantity called h, which is the delta L upon L. The question which one naturally will ask is, do Einstein's equations which describe relativistic gravity have gravity wave solutions just as Maxwell's equations have electromagnetic wave solutions? And this was answered immediately by Einstein in 1916, who predicted gravitational waves as a consequence of general relativity using linearized gravity. He gave the famous quadrupole formula in 1918, which is the analog of the dipole formula in electromagnetism. It says that the strength of the gravitational perturbation is determined by the second time derivative of the quadrupole moment. And if you take this formula and apply it to a system of mass m moving with velocity v, you get a very simple expression which you can calculate for a dumbbell made up of two trucks which is rotating at about a kilohertz. And this value comes out to be 10 raised to minus 39. Einstein, being a patent office clerk, essentially realized that it will have vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. And as usual, he was right, because it took us 100 years to make the first discovery of gravitational waves. For the next 50 years, there is a lot of confusion about the nature of gravitational waves. The physical question you asked is, do gravitational waves transfer energy, or they are merely an illusion because of the choice of wavy coordinates? It took 40 to 50 years for a conceptual framework to determine without ambiguity if gravitational waves exist in general relativity and what are their properties. The problem was resolved in a famous meeting in Chapel Hill in 1957, and the discussions between Pirani, Bondi, and Feynman essentially concluded that the tidal effect of gravitational waves are unambiguous, and therefore the physical nature of gravitational waves is definitely established. Once this was done, the treatment of gravitational waves in the full nonlinear general relativity was achieved by Bondi and his group and by Chandrasekhar. In this meeting, there was Joe Weber, and he suddenly sort of realized that if gravitational waves exist, one should build a detector to look for gravitational waves. And he went on to build what are called resonant bar detectors to look for gravitational waves. The sources he looked for were violent events like the supernova, and this really was the first generation of gravitational waves. It took another 50 years for the detection of gravitational waves to happen, and this involved the transmission to two paradigm changes. From resonant bar detectors, one had to move to laser interferometers. This gave us an advantage that unlike the bar detectors, which are narrowband detectors, the laser interferometers are broadband detectors. And the sources which one looked for were not supernovae but coalescing compact binaries. This was a revolution by itself because in 1974, Hulse, who was a graduate student, and Taylor, who was his advisor, discovered a dumbbell in the heaven made up of two neutron stars. This event was a watershed event because it demonstrated that gravitational waves are physical, they are accurately described by Einstein's general theory of relativity, and coalescing compact neutron star binaries would be prototypical sources for laser interferometer gravitational wave detectors. Simple physics will tell us that the signal from such a system increases in frequency and amplitude during the inspiral until it plunges at the innermost stable circular orbit. The gravitational waves from such inspiraling compact binaries, and then these compact binaries will coalesce and merge. The gravitational waves at these final stages have just the right kind of strength to be detected by gravitational wave detectors on the Earth. So if you do a simple example of such a system in the nearest cluster of galaxies, which is the Virgo cluster, the value of H comes out to be 10 raised to minus 21. It's not 10 raised to minus 39 as we had for gravitational wave sources in the laboratory. So if you can build an interferometer which is a kilometer scale long, the amount of displacement this train will cause is of the order of 10 raised to minus 18 meter. This is 1,000th of a Fermi, and therefore if you want to discover gravitational waves, you have to measure this very small strain and this very tiny displacement. So we can say that the laser interferometer is acting like a transducer. It is converting the gravitational wave to a photocurrent, which is proportional to the strain amplitude, and by measuring the small photocurrent, you can detect gravitational waves. To understand the challenge involved, let us just compare it with what happened in the Michelson-Morley experiment, which you learn in special relativity. The displacement it measures is of the order of a nanometer. And as you can see, we really have to measure 10 orders of magnitude smaller displacement. And therefore, if every 10 years you improve your sensitivity by a factor of 10, it's not surprising that it took 100 years to really make the measurement of gravitational waves by the technology which existed in the present day. There's another challenge which happens if you're trying to measure a very small amount, which is smaller than a nuclear dimension, but the detector is sitting on the Earth, and the Earth is susceptible to seismic motion. The seismic motion is of the order of a nanometer, and therefore you really have to damp the seismic motion again by a factor of 10 raised to 10. So there are two factors of 10 raised to 10 which you have to control if you really want to detect gravitational waves. You have to damp the ground motion by a factor of 10 raised to 10 and build a detector which can measure displacements which are much smaller than what was measured by the Michelson-Morley experiment. Even though you have a detector and a source, the challenges still continue because gravitational waves are weak signals and they are buried in the large noise of a detector. So you have to really appeal to engineers and use techniques which are called match filtering, both to detect the signal or extract it from the noise and to estimate the parameter or characterize the source. So what is shown here is really in blue the signal which is buried in the noise, and if you really want to detect it, as I said, you have to do match filtering. What is match filtering? Match filtering means correlating the known signal with the noisy data. That means you multiply the noise by the data by a known signal and then ask for integrate. That means you do the correlation. Now you will see that as long as the signal does not match with the template, there is no correlation. But once it matches, you pick up a correlation. So even though the signal is weak, the correlation can be unambiguously taken out, and it tells you that buried in the noise is a signal which is indicated in blue. So the important point is that we don't know what is the parameters of the source. So you cannot work with only one waveform. You really need to build a template bank, as they say. And the other thing which you need to do is, if you want to succeed in using mass filtering, you should be able to predict your equation, your signal as accurately as possible. Predicting what the signal is from a neutron star binary or from a black hole binary is what my research was sort of really involved in. And in collaboration with my colleagues in France, Blanchet and Damour, we basically constructed the theoretical model of what the waveform will look like if two neutron stars go around each other and merge, or if two black holes go around and merge. Once you have detected this particular signal, the signal depends on 15 parameters. So if you want to find out what are the parameters of the signal, and hence what are the parameters related to the source, then you have to do statistical techniques which are called Bayesian inference. So what is shown here is that in blue there is a data which is seen by the detector, and in the brown are theoretical waveforms whose parameters you are sort of varying. You are changing the mass, then you first change the distance, then you change the mass, and then you try to match your theoretical waveform with the data which you are getting from your detector. This tells you what the parameters of the signal are, and once you know what the parameters of the signal are, it tells you what is the source you are seeing. Is it a binary black hole? Is it a binary neutron star? What are the masses? What are their spins? What is the distance of the source? What is the position in the sky? And so on. So this is the game you play. You do match filtering to detect the signal, and then you use Bayesian inference to detect the parameters of the signal. The LIGO project, when it was conceived, people realized that if you are going to detect something so fine, you better be sure that you are detecting a signal and not some spurious noise from the detector. So they decided to build two detectors and put them away as far as possible in the US, one detector at Hanford and another detector at Livingston. The detectors are 4 kilometers long, and if you see a signal in both these detectors, you know that you are not seeing an environmental disturbance but an astrophysical signal. The initial LIGO consisted of two sites, but at the Hanford site there was two detectors. So we had a project which had two sites and three detectors. The other important point is the Europeans had their own detector called the Virgo detector at a place called Cshama near Pisa. And this is important because the gravity wave detectors are like our ears and not like our eyes. So it can sense signals from all directions. So if you really want to localize an astronomical source, you have to use triangulation between the three detectors which exist, the LIGO detectors and the Virgo detectors. So you essentially require a global detector network to really localize sources. If you do a simulation and ask what is the signal which you will have if you put sources in the various parts of the sky and try to localize them by using the LIGO detectors and the Virgo detectors, this is how the sources are. These sources are localized, but sources which are close to the plane are not localized well. They are poorly localized. On the other hand, if you take one of these detectors and move them to India, the sky localization becomes much more better over most of these regions in the sky. For example, one can show that if you have a detector not in Hanford But in LIGO India, the angular resolution improves on an average by 4 times and in some directions by a factor of 10 or 20. So this is really the motivation to have the LIGO India detector. And then what really happened is a story from the Indian side. In 2009, we realized that there was a revolution going to happen, and therefore, if we really wanted to be a part of that revolution, we should all come together in the national level and have a consortium, which is called the Indigo Consortium. The plan was to extend the Indian footprint in source modeling, which was in my group and RRI, and the work on gravity wave data analysis in Ayuka under my distinguished colleague Sanjeev Durandar. For 2 decades, we were working in theoretical aspects. So we realized that we should also have an Indian detector, and that is why we basically had set up the Indigo Consortium. So in 2011, when the opportunity came from the LIGO detector to host a LIGO detector in India, we made the LIGO India proposal and joined the LIGO scientific collaboration. This was very important because in the next 5 years, something remarkable was going to happen. And that was the first discovery of gravitational wave and the breakthrough which really happened immediately afterward. The first observational run was called the O1 and it involved the LIGO detector, which was the advanced LIGO. The second observational run involved both the LIGO detector and the Virgo detector. Just 2 days after the LIGO detectors were switched on 15 September uh, 2000, on 14 September 2015, the two detectors saw a signal, and the signals had exactly the same signature, so it was clear that they were signals from the same source. And this was the first detection of gravitational waves. One should keep in mind that it was not just the first direct detection of gravitational waves, it was the first detection of a binary black hole that merges within the age of the universe, because you are seeing the signal when the binary black hole is merging. It was the first observation of a stellar mass black hole whose mass was much higher than the mass seen earlier. The mass was more than 25 solar masses. If you ask the question, how can you make such a massive black hole, then it immediately tells you something. It tells you that this black hole was made in an environment where the stellar wind was very weak. And if you have weak stellar winds, it means that the metallicity of the medium is very low. It is made up of only things like hydrogen and so on. It came from a binary black hole which was at a cosmological distance. The distance was about 410 megaparsec. And even with this first detection, by looking at that waveform, we could test general theory of relativity in a regime where it was not tested before. So you can see here that it was not just about detection of gravitational wave, it was about doing astrophysics by using this gravitational wave. The discovery paper, which came out on 11th February, had 37 authors from the Indian institutions and citations to seminal papers, which included Indian researchers. The notable among them were Vishweshwara and the work done at Ayuka and at RRI. It was an important epoch for us because 1 week after the discovery of gravitational waves, the in principle approval of LIGO India was given by the government, and the basic institutions involved in this LIGO India project were RRCAT, IPR, IUCA, and DCSCL. This discovery was an important one, and therefore the three important people related to the project, Barry Barish, Kip Thorne, and Rainer Weiss, they were awarded the Nobel Prize in 2017 for contributions to the LIGO detector and for the observation of gravitational waves. It's important to keep in mind that Kip was the theorist, Rainer Weiss was the experimenter, but it also involved putting together a large team the LIGO scientific collaboration, and this was done by Barry Barish. The detection of gravitational waves is celebrated as one of the greatest scientific achievements of all time, and therefore these two observatories have been declared as historic physics sites. In that same year, as soon as gravity waves were discovered, a commission on gravity wave astrophysics was set up by the International Astronomical Union. So you can see here that the detection of gravitational waves also triggered the start of gravitational wave astrophysics, which is very unusual. It takes a few decades before detection becomes a subject, but it really happened in the case of gravitational waves. The second observational run began on 30th November, and in its last month, Virgo joined the search for gravitational waves. A fortnight later, the three detectors made their first discovery of gravitational waves from a binary black hole. And as expected, the sky localization, because the Virgo detector was involved, reduced from 1006 almost 1,000 square degrees to 60 square degrees. So the having a detector far away definitely helps you localize the sources, and this was proved already when Virgo came online. Another remarkable was just going to happen. The Nobel Prize was announced on October 3, but on October 16, the collaborations made the announcement of what we can call the spectacular launch of a multi-messenger astronomy. You saw gravitational waves from the LIGO detector and the Virgo detector, but the gamma ray detector called Fermi detected also from the same region in the sky gamma ray bursts. So you have a gravity wave being emitted from a source, a gamma ray burst emitted from the source from the same region in the sky, and a phenomena called kilonova, where you saw electromagnetic, optical, infrared, X-ray, and gamma radio emission from that same region in the sky. So we are seeing gravitational waves from a neutron star system. But as I said, it also gave you electromagnetic waves from the same source. It supports the hypothesis that the gravity wave source was produced by the merger of two neutron stars in a galaxy NGC 4993. It was followed by a short gamma ray burst, and then, as I said, a kilonova, which is powered by radioactive decay of R process nuclei, which are synthesized by the ejecta coming from this particular collision. We could put limits on the tidal deformability of these neutron stars, and this work was published in a PRL in 2017. Elements like gold, platinum, uranium, we think that they are all very easy to form, but it's not so. How are these very heavy elements formed? People thought that they are formed in supernova outbursts, but it turns out that the supernova happens so rarely that you cannot establish the abundance of these elements. However, in a neutron star merger, a lot of neutron stars are produced, neutrons are produced. There is what is called as the R process can happen, and therefore you can produce a large amount of silver, gold, platinum, uranium, and so on. So today we believe that neutron star mergers are the source for most of these heavy elements which we see in the universe. The importance of this body, of this observation, is sort of important because almost 1800 papers have been written on the observation, interpretation, models of this particular object. And even as late as 2023, interesting observations of this particular object continue to emerge. So you can see here that this object established a multi-messenger time domain astronomy, and it basically emphasizes the importance of having collaborative gravity wave, electromagnetic, and neutrino observations in the future. In addition to this, the binary neutron star helped us do cosmology because it allowed us to measure the Hubble constant in an independent way. And as you know, there is something called the Hubble tension, two different ways of determining the Hubble constant, one by the cosmic microwave background radiation and another by supernovae, don't match. The observation of gravitational waves from this binary neutron star helped us and give an independent measurement of the Hubble constant, basically because of the fact that gravity wave observations give you the distance to the source, the electromagnetic observations provide the redshift because you know in which galaxy this is, and you know the electromagnetic observations from this particular source. Therefore, putting this together, you can measure the Hubble constant, and what is shown here is an independent measurement of the Hubble constant. So you can do cosmology also by using these binary neutron star systems. The amazing thing is that Einstein's general theory of relativity can be tested in a dynamical strong field regime. Many different aspects of this can be tested by this particular object. For example, you know that the gravitational waves and the light, electromagnetic radiation, came at roughly, very close to each other. So it basically tells us that gravitational wave speed is almost close to the speed of light. Many other predictions of general theory of relativity, like tests of Lorentz invariance violation, whether dipole radiation is being emitted, are there extraspatial dimensions, many such predictions of general theory of relativity can be sort of confronted from the data, and this was also sort of done by the collaboration. So, at the end of this particular second observational run, the vision of our universe is as follows. Before gravitational wave observation, we had looked for electromagnetic radiation from pulsars or neutron stars and X-ray observations from black holes. This is how the picture looked like. But the moment we made gravity wave observations, suddenly we saw black holes which were more massive. We saw a neutron star system which was different from the other electromagnetically observed pulsars. So you can see here that what we are really seeing just in these first observations itself is a justification of the O which is there in LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory, and it is a amazing thing that even before gravitational waves were detected, the people who wrote this proposal had the courage to call it an observatory, that we would be able to do astronomy once gravitational waves were discovered. And the whole subject has been very transformative because in the first discovery itself, you have discovered a new class of black holes which are heavier than the earlier black holes, and a gamma ray burst which was short gamma ray burst which was subluminous. Gamma ray bursts which were seen up till then were not as luminous as as subluminous as this. So at the end of the observational run, we put together our catalog, which had 10 binary black holes and one binary neutron star. Once we make the data public, other groups can also look for gravitational waves within that particular data. The Princeton group was one such group, and in our data, they also discovered 8 new black holes. So you can see here that there is an opportunity to look at the data once it's made public and look for gravitational waves which the collaboration may have missed. This essentially finishes the second part of my talk, which basically talks about the discovery which really was made and the revolution which really has happened. The picture which emerged was consolidated in the third observational run, which began on 1st April and ended on 30th September 2019. The second part of it was supposed to began on 1st November and was supposed to go on till the end of April, but because of the pandemic, the observatories had to be closed. The Kagura detector in Japan was supposed to join at the end of 2019, but they could not join. But then what really happened was in April 2020, for a fortnight, the Kagura detector and the geo detectors made joint observations. The data from this particular observational run was made public on 5th November 2021. In the third data run, we did a lot of things. We gave what we called open alerts so that astronomers could look for electromagnetic and neutrino counterparts from our gravity wave events. From the data, we tried to identify exceptional events. We created a catalog of gravity wave transients with all their parameter values. From this population, we can predict what are the rates of these events, what are the properties of this population, what are the formation channels of these objects. Can we test general theory of relativity using these observations? Can we do cosmology by using these observations? Can we look for signatures of gravitational wave lensing and look for other kind of sources like supernova sources, fast FRBs, and so on, and to see whether exotic sources like cosmic strings also are present in our observations. So you can see a lot of things can be done from the data which we extract out from these LIGO and Virgo detectors. And as I said, the public alerts are amazing because they are what are called low latency alerts. As soon as we detect some event, in about a couple of minutes, we send out a preliminary alert. Then humans look at the data, make an estimate of the parameters, make a classification, and within a couple of hours, send out either an initial alert or retract the preliminary alert. Then, in a few days or in a week, we estimate the parameters more accurately and then send it out to the community. This is how we collaborate with the astronomers and look for the electromagnetic and neutrino counterparts of our gravity wave event. So as you can see here, in the first two observational run, we had about a dozen sources. But because the detectors are more sensitive, we could detect a total of 79 sources in the O3 observational run. So the catalog now consists of about 90 sources. Once we made the detectors, the data public, other groups looked for gravity wave sources, and again, indeed, the two different groups found additional sources in our data. So the picture looks like this. If you really look at the coalescing compact binaries, they are a different population from the sources which are seen by electromagnetic observations. By electromagnetic observations, these are the neutron stars which you look at. These are the black holes which you look at. But the black holes and the neutron stars which are seen by gravitational waves are a different kind of population. If you look at the exceptional events, interesting events were sort of seen. We saw, for example, the second binary neutron star. We saw a neutron star black hole system. We saw an intermediate binary black hole system, asymmetric binaries, so that subdominant modes could be seen from their observations. There are situations in the mass which are called mass gaps, a lower mass gap and an upper mass gap. and we saw hints that maybe there are systems in these mass gaps. So, because we could determine the parameters of this particular system, we could see a big variety of binary black holes, binary neutron stars, black hole neutron star systems, and therefore we are really seeing a new class of objects which could never be seen by electromagnetic observations. Because we are seeing a population, now we can make a prediction. We can say that the binary black hole rate is something like 18 to 44 per gigaparsec cube per year. Similarly, the binary neutron star is something between 10 to 1700, and for the neutron star black hole, something between 8 and 140. So, this is something which basically tells us if you see more parts of the universe, you will be able to see more and more such events. With that, I come to the current status, which is the fourth observational run. The fourth observational run began on 24th May 2023 and ended on 16 January 2024. It involved only the LIGO detectors because the Virgo detectors had some problems, so they could not be turned on. The second part of the O4 run began on 10th April and will go on till February 2025. There is talk of probably extending it up to August 2025 if possible. And this involved, as I told you, the LIGO detector and the Virgo detector. And a little later, when their sensitivity improves, Kagra will also sort of join before the fourth observational run ends. And now, because the detector is more sensitive, you can see that even beyond the third observational run, more events have been sort of seen. In the fourth observational run, 81 events have been, sort of candidates have been identified. Already 18 candidates have been identified. Remember, I am not calling them events, they are just candidates because we are still determining all their parameters. When we determine all the parameters and make sure that they are astrophysical events, then they will be called gravity wave events. And that is what is currently happening. We sent out observational alerts, but our latency alerts are, yeah, before I do that, let me also sort of mention, we saw an interesting event which we on 20, which is called GW23529. It's an interesting event because it's a neutron star black hole event which happens in what is called as the mass gap. The lower mass gap is the following. We believe that neutron stars are less massive than 3 solar masses and black holes are more massive than 5 solar masses. It was sort of believed that between the 3 solar mass to 5 solar mass, no black holes could be really found. But now, in this particular case, we seem to have seen an object which has all the characteristics of a black hole, but it lies in the lower mass gap. So as you can see here, in every observational run, we are coming up with objects which we never imagined existed before. I've been talking about all the coalescing compact binaries made up of black holes and neutron stars, but that is not the only kind of observations which we do. We basically look for gravitational waves, as I told you, from supernova remnants. These are unmodeled kind of sources or from fast radio bursts. So, from burst events which are unmodeled, we look for gravitational waves. We look for gravitational waves from single neutron stars. These are pulsar, these are long duration gravitational waves. And from stochastic background, even though we cannot detect the gravitational waves from a single neutron star, a family of neutron stars will create an astrophysical background, and this is called the stochastic background of gravitational waves. We look for stochastical background of gravitational waves both from the cosmological models and from astrophysical models. So as you can see here, what I told you is just 1/4 of the story. There is other part of the story which also you can hear about in other talks. from other experts in the collaboration. With this, I go to the future prospects. In the future, as we know, in addition to the Kagra detector, the LIGO India detector will come online. And once the fourth observational run finishes, the fifth observational run will begin somewhere in 2028. Just see the change which has happened. In the third observational run, we saw one event per 5 days. In the fourth observational run, we are seeing one event in roughly 3 days. By the time we go to the fifth observational run, when the detectors become more sensitive, we will be seeing 3 events per day. So you can see here that suddenly the population of gravitational coalescing compact objects will increase dramatically, and therefore our picture of the coalescing compact boundaries will become more robust. The collaboration has plans. For example, currently the detectors are in what is called as the A plus configuration. Beyond that, there is something called the A sharp, and then technology development creates what is called as the Voyager detector, and then finally the explorer, which is called the Cosmic Explorer, which is a 40-kilometer long interferometer. So let us just see what is the plan for the Cosmic Explorer. So as I told you, by 2026 we'll be in the A plus configuration, which can see neutron stars up to 325 megaparsecs. By 2029, the A sharp is proposed, which can see neutron stars up to 600 megaparsecs. But the Cosmic Explorer, which has 10 times more sensitivity than the A plus, will be a detector which is 40 kilometers long and 20 kilometers long, two such detectors. And by achieving a sensitivity 10 times more, they will really see all the neutron star surges which happen in the universe. Why are we trying to understand all the neutron stars and all the black holes in the universe? The basic science drivers of the next generation observatories are the following. We want to study gravity in its extreme form. We want to study matter when it's subject to extreme densities and pressures. And finally, use them to understand cosmology and understand cosmic history. So, the four themes for the next generation gravity wave observatories are to understand black holes and neutron stars across the full universe, understand the physics of dense matter and multi-messenger astrophysics, understand probe cosmology, and also use it to understand the dark sector of the universe, and finally, understand the impact of gravitational waves on fundamental physics, and to look for sources which are novel, which we have not imagined up till now. With the third generation detectors, you will detect a significant fraction of all the CBC mergers which happen in the physical universe. So you can see the neutron stars till the edge, the black holes till the edge of the universe, and therefore you can detect the mergers of the first stars which formed because of the primordial black holes. So when the early universe, in the early universe, fluctuations of the matter which is there can create primordial black holes, and the cosmic explorer can look for these kind of primordial black holes. The Europeans upgrade their Virgo and are going to create what they call the Einstein telescope. This is a 10-kilometer long detector which is underground. It has a triangular configuration like the LISA detector. It has two interferometers, a low frequency detector and a high frequency detector, which are put in a triangular configuration underground. Because you go underground, you have better control over the seismic noise, and therefore you have better low frequency sensitivity. Two sites have been identified in Europe, one in Italy and one in Netherlands, where this triangular detector may be put. There is also a recent article in Nature which basically says that maybe both these sites will be chosen, and the low frequency detector may be put in one side and the high frequency detector may be put in the other side. So you can see here that ambitious projects are online to look for the next generation of gravitational wave detectors. What happens to our detector in India? As you know, the site has been identified at Aunda. Our colleagues in IPR have done vacuum prototyping. At RRCAT, a facility to build a 10-meter prototype has been set up. Colleagues in IUCA have set up a computing facility, build up a team to build expertise for setting up the LIGO India detector. There is a lot of EPO activity which happens. This is one part of the EPO activity which is happening right now. And our colleagues, for example, in AstroSat, Varun Bhalerao, has proposed the Daksha project to look for X-ray counterparts and for the gravity wave sources. So, because of the fact that the gravity wave theory, data analysis, and the gravity wave experiment should come together, the Indigo Consortium was called the LIGO India Scientific Collaboration in 2019. It's interesting that last year we finally had the full approval of the LIGO India project, and the LIGO India project is supposed to come online in 2030. When the scientific merit of the cosmic explorer was explored, people also took into account that there is a new LIGO detector which will come online in 2030. And when the science study was made, it has been shown that the availability of the LIGO India in the next generation network post O5, it is very important for multi-messenger astronomy. So, in the third generation detector also, LIGO India has an important role, and that is very exciting for people in the audience because LIGO India is not just the beginning in 2030, up to 2040, LIGO India can play an important role. But the important thing is that we should come online by 2030. We should not miss the bus one more time. The LIGO India Scientific Collaboration is a 15 collaboration with about 117 members. And the PI of this is Archana Pai from IIT Bombay. Let me remind people that LIGO India is not just about astronomy and theory. There is a lot of experimental aspect, a lot of technology involved. And since these technologies go beyond LIGO India, I expect that if LIGO India comes online, the technologies will play a role in other fundamental experiments which will happen in India. For example, quantum metrology can improve, laser physics can improve, vacuum technologies, our expertise can improve, optical engineering, sensor technologies, control system control aspects, all these things will improve if LIGO India comes up as a successful project. As one of our colleagues basically said, LIGO involves technologies, and every technology they are touching, they are pushing, and there is a lot of technologies they are touching. I talked about gravitational waves from detectors on the Earth. These have detectors whose frequencies are, whose time duration is of the order of milliseconds. But if you go to, there are other gravitational waves. For example, if you look at gravitational waves from supermassive black holes, then they are in the range of millihertz. If you look at gravitational waves from pulsar timing arrays, they are in the nanohertz range. and gravitational waves from the Big Bang is at the attohertz range. So one has to keep in mind that just like in electromagnetism, there are 2 decades in frequencies that gravitational waves cover. Last year, interesting results happened. In the nanohertz range, strong evidence for gravitational waves was sort of discovered. And these were again many consortia, nanograv, PPTA, EPTA, and excitingly, there is a group in India, the Indian Pulsar Timing Array, which was also part of this great discovery. The GMRT, the UGMRT data was used in these kind of gravitational waves. And as I mentioned, these are gravitational waves from the stochastic background of supermassive black hole binaries. In January, another exciting thing happened. The LISA mission has been formally adopted by ESA, and the construction will begin next year, and the launch is supposed to happen in 2035. The LISA consortium is already formed, so anybody who wants to contribute to LISA science can join this consortium and participate in gravitational waves in the millihertz range. So you can see here that there is a revolution out to sort of happen. Gravitational waves by detectors on the Earth, gravitational waves from pulsar timing arrays, gravitational waves from LISA in the 2035 epoch, all this is waiting to happen. And as I basically say, there is a wide way of gravitational wave sources from where you can look for gravitational waves. So currently we are looking for gravitational waves from known knowns or known unknowns. But the challenge, of course, is finally gravitational waves from unknown unknowns. And this always happens. You begin from somewhere, but you will end up with something which you didn't know about. So therefore, the Gravitational Wave International Community put forward a roadmap for where the subject will develop in the 2020s and in the 2030s. And this is a very nice article in Nature Review Physics, which you can look up for where we plan to go in the coming decade and in the next decade. So I come to my concluding remarks. The next generation gravity wave network will have a transformative impact on the nascent field of gravitational wave physics and astronomy. It will lead to an era of precision gravitational waves and multi-messenger astrophysics. There is a tremendous discovery potential in cutting-edge research because we'll probe gravity, black hole formation, and their evolution to the beginnings of star and galaxy formation and potentially to the early moments of the universe. It enables profound quantitative probes of QCD and neutron-rich matter, Hubble tension in cosmology, new physics, because we will be able to say something about the dark matter and dark energy content of the universe. The scientific impact will go beyond gravity wave astrophysics and will touch fundamental physics, particle physics, and nuclear physics. The sensitivity, which is unprecedented, will lead to major technology advances in advanced electronics, material science, quantum sensing, and quantum information science. Therefore, the faint strains of the gravity wave symphony are whispers of a new revolution. Therefore, all of you young people in the audience, I invite you to decipher the universe using gravity wave observations and multi-messenger astronomy. Each of these blobs here is a discovery waiting to be made and a Nobel Prize to be waiting to be won. So thank you for your attention, and I hope you will join this interesting search in the coming future. Thank you very much for your attention.
Yeah, thank you so much, sir. You can see the claps behind me and some online emojis also. Wonderful talk as usual, very captivating and very informative for the younger generation. We've given lots of points for them to look into. Now, time for questions. The part people who are online, they can raise their hand and I can invite them to unmute and ask the question. So yes, Hitanshi, you can. Go ahead with your question. Hitanshi. If not Hitanshi, then it's Ritabrata Mukhopadhyay.
Hello,
Yes.
am I audible?
Yes.
Yeah, you just said it in one of your slides that using the gravitational wave, you have discovered a black hole that was not supposed to exist on the mass cap that you mentioned. Theoretically, it was not supposed to be there, but you found evidence of the black hole being found in that mass cap.
Now, what is your question? Can you repeat it?
Yeah, I want to ask like what is the application of finding such black holes? You just found a black hole that was not supposed to exist in that mass cap, and now you have
Correct.
found it. But
Yes.
how does it connect that to some, as you have been saying that this connects to different fundamental physics discoveries, but so far, how much progress has been made in that field? Just
So,
keeping on
so the
discovering
point
gravitational waves.
is, based on what we know before, we make some speculation, and based on the observations which exist at that particular time, we see consistency and believe that there is a fundamental reason why something should happen. So finally, observations are the test. And if we see more and more black hole systems in this particular gap, it basically will mean that there is no such thing as this gap. Black holes can exist even below 5 solar masses. So it basically increases the parameter space in which black holes can exist, and therefore it challenges you to create paradigms for making these kind of black holes. So that is how astrophysical modeling needs to be improved. And in that astrophysical modeling, some fundamental aspects of physics will also go into it. So you'll get insights into the fundamental physics which go underlie the astrophysical modeling of these kind of systems. That's what I meant.
All right.
Right. Other question? Do we have any question from the audience? Yeah, please come. It's difficult. I cannot ask your question.
हेलो सर।
Yes.
सर एक्चुअली हम अभी मतलब देखा कि इलेक्ट्रोमैग्नेटिक वेव्स और एक्सरे ऑब्जर्वेटरीज से वो जो हाई मास जो ब्लैक होल्स है वो
हाँ.
हम डिटेक्ट नहीं कर पा रहे थे, पर ग्रेविटेशनल वेव्स से कर पा रहे हैं, ऐसा क्यों?
So what is your question? आपका प्रश्न क्या है?
Yeah, so his question is basically he's asking that we were not able to detect the black hole using the electromagnetic observation, and we
Right.
have been able to detect them using gravitational wave observation. Why? He's asking. I mean, is there any specific reason?
So, what happens in science is when you make a new discovery, the new discovery adds a new question, and that's how research grows. So, what this really means is the kind of processes which lead to black holes, which can put out electromagnetic radiation, those kind of processes seem to be absent when the masses are much larger. So we'll have to look at mechanisms which form low mass black holes where there is an electromagnetic counterpart, and there is the other kind of black holes which you can see only by gravitational wave emission. So it is really posing a question, and the fact that for many years, even though we are making X-ray observations, we have not seen these kind of black holes. It really forces us to ask the question: why is there no X-ray emission from these more massive kind of black holes? Or is the X-ray emission so weak that when we have a more sensitive X-ray detector, we may see emission from them? So what the answer is really something which we will have to wait and see.
Right.
I'm sorry I could not give this answer in Hindi. My Hindi is not good enough to say that, but I hope
No,
you understand the answer.
no, that's fine, sir. We understand. Roshan has a question. Yeah, please.
Good evening, sir.
Yes.
My question is, as we can see in the slide, that Daksha is also building, like, so working as a counterpart of gravitational waves.
Right.
Is gravitational waves and electromagnetic waves emit at the same time, or there is a delay? Okay, that we know that it's travel the speed of the light,
Yes.
but it's found that it's a bit delay. And what's your comment on that?
Yeah. So the point one has to keep in mind is, if Einstein's theory is right, the speed of gravitational waves must be exactly the speed of light. Okay. And as you rightly point out, if you can see electromagnetic radiation and the gravitational radiation coming very close to each other, using the difference, you can say that the difference in speed is only of the order of so much, 10 raised to minus 15 or 10 raised to minus 16. So, as the observations get more and more distant, for example, if the source is even further away, the limit which you can put will be even more stronger. So this is what will really happen, that as we see more and more distant sources which are emitting both electromagnetic and gravitational radiation, we will be able to put a bound on how close the speed of gravity is to the speed of light. But it could very well happen that the theory of gravity is not Einstein's theory of gravity, but some massive gravity where the graviton has a very small mass, exactly like in the case of the neutrino, where the neutrino was supposed to be massless, but now we know that the neutrino has a very small mass. So that same thing could happen in the case of gravity also, that maybe the graviton has a very, very small mass, and therefore there is a fundamental difference between the speed of gravity and the speed of light. So these kind of questions will be addressed as we make more and more sensitive observations.
Right. Yes. Yeah, you can ask. Ah.
So the frequency range of an LIGO detector and
I cannot hear you clearly.
Yeah, please, you will have to come here. Yeah.
So, my next question is the frequency range of LIGO detector nowadays and
Right.
upcoming third generation gravitational wave detector. The max frequency range is around, both of them are around 2K kilohertz.
Correct.
So they are more or less the same. So when the third generation LIGO detector will be there, so that ground based detector will be there, so that LIGO detector will be useless, or there's something special about.
Yes. So here, there are complicated things related to funding, etc. So what will happen is the LIGO detectors, which are currently existing, they have been functioning for many, many years, and there's a lot of breakdown, etc. To keep these facilities running costs millions of dollars, and therefore what will happen is eventually when the Cosmic Explorer comes on, the LIGO detectors in the US will be decommissioned. And coming back to your question about the frequency, the Cosmic Explorer, there are two the proposed detectors. One is 40 kilometers long and one is 20 kilometers long. And the 20-kilometer one is basically designed so that it has more sensitivity at the higher frequency and can look for the neutron star final states. So the proposal of the Cosmic Explorer is based on the scientific cases which need to be addressed by the next generation detectors, and they have tried to do a science audit, try to study all the science, what are the system requirements, so that all scientific problems will be addressed over the next couple of decades, and they have made the proposal taking this into account. In the reference which I quote, the NSF report, all these things are very detailed mentioned. So you may just want to have a look at them.
Right. But, sir, we will need those detector which can detect the gravitational wave signal in the late merger, right? And the
Correct.
frequency is of the kilohertz.
Correct.
That's where we can test the strongest field of it.
Exactly.
right?
You'll be able to say, what happens to the final states of neutron star mergers.
Yeah,
You can get some radiation from, specific F modes, etc. Some specific radiation modes from the higher end can be sort of seen, and they will conclusively tell us that the final remnant is a black hole or a neutron star. So it's very important to study the high frequency part of the gravitational waves.
right,
And just to sort of mention, the Australians really wanted to target this. So there is also a proposal by the Australians to build a high frequency third generation detector. But everything costs money, and therefore the final challenge is being able to find the funding for the next generation detector.
right. So maybe time for one last question from people offline or online.
I just wanted to add one thing about LIGO India. As I keep mentioning, the two LIGO detectors are older detectors. The LIGO India detector is a new one, but it is exactly like the LIGO detector in the US. So even if the LIGO detectors, the two LIGO detectors are decommissioned, the Indian detector, if it comes on in 2030, will be a clone of the LIGO detectors and therefore can contribute to multi-messenger astronomy in a very, very important way. So that is really one reason why we should make sure that LIGO India succeeds tremendously and comes online by 2030.
Right, at least for 10 more years after
Yeah,
commission.
2030 to 2040 is when there is a big chance to make breakthroughs for us.
Right. So any other questions? Yes, Abhishek. One last question from Abhishek, sir.
Sir, I wanted to ask one thing that the gravitational waves produced by stars may be coming from similar mass sources. Will be there any kind of difference in the nature of the wave according to the nature of the stars? So that from observing the gravitational wave, we can make any kind of comment on the nature of the star which is producing it or the type of the source behind it.
Yes, so the point one has to keep in mind is, the frequency range of the gravitational waves depends on their compact, how compact they are. So if you really take a star, even if you take a star like the white dwarf, the frequency of gravitational waves from a binary system made up of white dwarfs falls in the millihertz range. So by ground-based detectors, you cannot say something about it. So what really happens is that even though in principle, if you have a rotating star, it will emit gravitational waves. The strength is going to be so much weaker that it is not probably being able to say something about the nature of the star.
Right,
But you can say, as we have been saying, we can say something about the nature of the black holes, the nature of the neutron stars from them, and there seems to be a big variety of those objects also. So the what you are saying for stars can be done for black holes. Unfortunately, we cannot do it as much well for stars.
okay. So any other questions? Reeth is there. Reeth, if it is a short question, then you can ask. Yes, please go ahead.
Uh, you mentioned in your slides that gravitational waves can help in finding out the nature of dark matter or dark energy. How will it help?
Yes. So one thing is, we have the we can do cosmology with these gravitational waves I mentioned. So you can try to look at the gravity wave observation and try to determine the cosmological parameters, the lambda for dark energy, the lambda for curvature, etc. So people are trying to now see how much can you do with the gravity wave observations and determining the cosmological parameters. That is one way of doing it. The other thing is, for example, some light bosons are supposed to be dark matter. These kind of light bosons can form clouds around rotating black holes, and one can look for gravitational waves from such systems. So, by looking at the gravitational wave limits from such systems, one can put a limit on the light bosons which may presumably exist around these rotating black holes. So that's how you put limit on the dark matter. Or, for example, if you can put some limit on the primordial black holes, then again people believe that the black holes might be primordial black holes may be one kind of dark matter. So if you can put a limit on the amount of primordial black holes which are consistent with the gravity wave observations, you are putting again some limit on the dark matter. So studies of this particular kind, by confronting the gravity wave observations with what the model they are consistent with, that is what helps you say something about the nature of dark matter and the nature of dark energy.
Right. Thank you, sir, for taking all the question and answer. Time to close up this session. I want to just make a comment. They say that electromagnetic waves are eyes to the universe, and these gravitational waves are now ears to the universe. But I have a problem. The eyes are very beautiful part of our body, but however, the structure of ears is not that good. I mean, if you want to show some picture of ears, I have seen it in some many articles. So that's the thing. If you could tell community, if you could think something else instead of saying it ears to some some other part of the body.
No, Guru, the reason one uses the ears is to emphasize the fact that if you have a gravity wave detector, it is sensitive to gravity waves coming in any direction.
Ah, right, yeah.
And that's exactly how a ear is.
Yeah,
You can hear something from behind our. So the
right,
antenna pattern of a gravitational wave detector is almost omnidirectional, almost from every direction. It is, of course, the sensitivity depends on from which direction it is coming, but you can pick it up from any direction. That is the strength of it. So
right.
while eyes are good, the ears warn us that
Yeah,
something dangerous is going to happen.
exactly, exactly. Yeah, in that case, we can deal with the not so pretty structure of the.
Exactly.
Okay. Okay, thank you very much, sir, for this wonderful talk, a wonderful interaction. You can see some slow claps from here. And I hope and I wish that you will keep inspiring us for many more years to come.
Yeah,
Thank
thank
you
you
very
all
much.
for coming to the talk, and I hope you have enjoyed the talk. So the future is all yours.
Exactly. They are the future. Thank you so much, sir.
Bye.
Good night. Bye
Good
bye.
night.
Sorry. राइट अच्छा मुझे हर बार उनका स्क्रीन पे आई स्टार्ट डूइंग